Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 2 of the spin devices. And as you may remember, in Module 1, we started by explaining this basic experimental fact, namely that when you have two magnetic contacts in parallel, just a non-magnetic channel, you get a resistance, this parallel resistance, which is less than the anti-parallel resistance. And what we have seen is that you can understand this by assuming that the resistance of the two spin channels, that is any channel that all channels have these two spin channels, which are identical. These are non-magnetic materials. These two spin channels have different resistances, small r and big R, depending on whether the magnet is in the direction of the spin or is opposite to the direction of the spin. Now, why that resistance is different, as I mentioned, we'll talk about later. Okay. Now, what I want to talk about this week, or rather in this module, is like what does the quasi-Fermi level or this electrochemical potential look like inside the channel? As you may recall, in the first few weeks when we were discussing current flow, we usually didn't talk too much about what happens inside the channel. We talked what is the conductance measured between contacts, sort of like what we did in the first module. On the other hand, I think it was in the third week and the last 2 or 3 lectures where I introduced this idea of the electrochemical potential, or in short what I'll just call potential, of how the potential varies inside the channel. And the basic equation that I'd written, if you may recall, in that context is that the current is minus sigma A over Q d mu dz, where this mu is this potential in the channel, and it has these two fixed values at the two ends and changes along the device, along the channel. And this is how you can find the current. And in a one-dimensional device, we discussed how di dz is equal to 0. And one could solve those two equations, because what it requires is I could take d dz of that quantity, and if the conductivity happens to be constant, then you'd get an equation that looks like d2 mu dz2 equals 0. That's what we had done in week 3, I believe, in one of the, I guess, 4th or 5th modules. That's where we talked about this. Now, so if you try to plot this across the channel, you'd have something like this. That you have one end of the channel, that's the source, where you have a mu1, another end, that's the mu2. So this is like the source, this is like the drain. And since the second derivative has to be 0, it means basically it will be linear across the thing. And so you have something like this. And then as we discussed, near the ends you always have these drops because of the interface resistances. So a good way to think about spins then, of what we're doing now, is kind of try to do the same, but for the two spins separately. So you've got something for the, we'll call the up spin, that's the red, and the down spin, say the blue. So you got two spins separately for which we have much the same story. So equation-wise, we could say that let us write I up is equal to sigma A over Q mu up. So there is a potential associated with the up spin, and there is a current associated with that. Now, as far as the conductivity is concerned, we are really talking about this non-magnetic channel. So you see, upspin and downspin basically have the same conductivity. So I don't really need to write a sigma up or a sigma down. But then I should divide this by 2, because when people write conductivity, they usually mean the conductivity of the two channels together. So when you have two things in parallel, that has a certain conductivity, but each one individually has like half the conductivity. So I put a 2 there. That's it. So using this then for the upspin channel, you could try to, so let us say we are talking about, right now, in this case, let's say we are discussing the parallel configuration. So the parallel means this is parallel here. And so you have for the red channel, you have a low resistance. For the blue channel, we have a big resistance. That's the capital R. And the question is, what does the potential profile then look like for the red channel and for the blue channel? And basically, each one would look something like this, because at this time we are saying up and down are separate. So it's almost like we're doing two separate problems for the red channel and the blue channel. But the red channel has a smaller resistance at the ends. And so this little drop at the ends will be relatively small. Whereas the other one, it would be relatively big. So it would look something like this then. So when I draw the red channel, I'll have a small drop here. At the two ends, but otherwise linear. Whereas when we do the blue channel, we'll have a big drops at the two ends, but again, otherwise linear. So, I guess I'll just try to draw this a little better. So, in the parallel configuration then, with the two magnets parallel, this is what you'd expect the potential inside the channel to look like, how it varies inside the channel. And the two currents are different, in the sense the blue current, you see, the slope is less, the red current, the slope is more, as you might expect, because after all, the blue channel sees a higher resistance, less current, red channel, lower resistance, more current, etc. Now, what does this picture look like for the anti-parallel configuration? Well, same basic equations, of course. It's still, we have for up or down, same equation. Sigma is the same. Instead of up, we put down. So, just two sets of equation, no change there. Question is, what would this picture look like then for the anti-parallel configuration? Well, now you can draw it something like this. You see, you have a mu1 here, mu2 there. This is the source end, that's the drain end. And when you look at the red channel, you see, now we are talking about the anti-parallel configuration. So what that means is, this is now a small r, that one's now a big R. So when you look at the red channel, you have a low resistance to the left, big resistance to the right. Blue channel, reversed, big resistance to the right, low resistance to the left. Okay. So now we want to draw this picture, and you can easily see what it would look like. Red channel has a low resistance on this side, but a big resistance on that side. So low drop on this side, big drop on this side. Whereas, if you take the blue channel, big drop here, low drop on that side. So this is what you'd expect the potential profile to look like in the anti-parallel configuration. This is anti-parallel, this is parallel. Okay. Now, this is fine, but one thing we have ignored in this discussion is that there are what are called spin flip processes. That is, you see, you've got these two types of spins, the reds and the blues, and they have two different potentials. And there's always all kinds of processes going on inside the solid which doesn't like this difference. They like to equate the potentials of all the different things. So if you have reds and blues with different potentials, it will try to make them equal. And so, in practice, often what would happen is that both of these, if this was relatively long, with lots of these spin flip processes, things that try to equate reds with blues, then what would happen is, if I draw a sort of an average line here, instead of these being separated all the way, what would happen is, this thing would tend to kind of join up there, and this would also want to join there. In short, there will be processes inside which would try to turn the reds into blues, so the red potential wouldn't be quite so high and the blue potential wouldn't be quite so low, but rather they would come together. And the same thing would happen sort of at the two ends. See? So physically that's what would happen, and a similar thing with the parallel case. But the main point I'm trying to make is that if you ignore spin flip processes, then it's very easy to see what happens. You just have two separate equations or two separate systems, a red system and a blue system. Think of them separately. That's it. On the other hand, if reds can convert to blues, as in all real systems, as long if it's only in very short things that you can ignore those processes. But if you have to take those into account, then what would happen is they would want to come together. And what I want to discuss in the rest of this module is how you modify the equations to handle that. You see, the equation that people use, that's what's known as the Valet-Fert equation. You see, that's what's on your slide there. And I'll try to explain where that Valet-Fert equation comes from. See, and what it does is includes these spin flip processes. So let me take off these pictures. Rest of the module, I'll be just writing a bunch of equations and trying to explain where it came from. But the idea is, those are the equations that if you solve them, you'd get these pictures, showing how they come together, for example. So, as I said earlier, we have these two basic equations. I up is so much, and there is a I down. I'll now write it separately. There's I down, which is identical, but it involves the mu of the down channel. Okay. So far so straightforward. Now, the part where we need to include the spin flip processes is this one. That is, I had argued earlier, you see, that in a one-dimensional channel, the current cannot change with distance. Why? Well, because the argument goes that if you have 20 electrons coming in per second from the left, and that's the current here, well, as you go down the channel, the thing is, a little later, it also has to be 20 per second going out. Whatever number comes in must be going out if you want steady state. Because if you had 20 coming in and only 10 going out, then of course electrons would be piling up here with time. And that wouldn't be a steady state situation. So steady state, whatever comes in, goes out. And so di dz must be 0. But now what we have is sort of two separate lanes. You have the red channel and a blue channel. So it's two separate lanes. And of course, if they don't talk to each other, then of course you have the same situation with both. You could say, okay, we'll just write it as d/dz rate of change of I up, we'd say is equal to 0, and the rate of change of I down is also equal to 0. Because we could, whatever I had said before for one channel, I could make the same argument separately for each one. But the spin flip processes, what it does is it takes reds and turns them into blues, and the blues back into reds. You see? So you have this intermingling of the channels. Things can go this way, and things can go up that way. So what that means is, of course, if I look at the full thing, that of course still must balance out. In other words, if I counted all the reds and blues that came in from here, let's say 30 of them per second, then together 30 per second should be going out there. So what that means is, the sum of those two things, d/dz of I up and I down, together must be 0. But individually each one doesn't need to be, because I could easily have a situation where 20 per second came in here, only 10 per second left on this side, but the other 10 converted to blues and went off that way. See? But then of course, this went down, but the flux in the blue channel must have gone up. And so, in general, what you could do is write d/dz of I up is equal to minus d/dz of I down. So the rate of change of I up is the negative of the rate of change of I down, which means the sum of the two doesn't change. So if I looked at the derivative of I up plus I down, that would just be 0. So d/dz of I up plus I down together, that is 0. So I could write it as this. Now the question is, these are equal, but what is this equal to? That is, how can we relate it to the potentials mu up and mu down? And this is where, of course, what you'd expect physically is, you see, again, thinking of this as cars on a highway. Let's say you have a lane that is jam-packed, lots of reds going along, very few blues. And then you say that, well, you are allowed to change lanes. What you'd expect is lots of reds would come over to the blue side, but not as much from the net flow would be from the red to the blue. So in other words, what you expect is the flow would be from the side that's relatively filled to the side that's relatively empty. And so what you might expect is that the rate at which things would go up from up to down would be equal to would be proportional to the difference between mu up and mu down. So if mu up happens to be bigger than mu down, then lots of up would want to go to down. What that means is the derivative of I up would then be negative, because a lot of them have moved over. So you'd expect this to be, there'll be a negative sign there. And what we'll do is, okay, and then I'll put a k there denoting some constant. That tells you just how easily spin flip processes convert ups into downs. The main thing I'm using a physical argument for is to say that this quantity is proportional to the difference and that there should be a negative sign there. Now, if you actually want to get this constant, what it is, how it depends on spin flip time, that requires a little extra discussion that we won't be going into right now. In general, as I had mentioned in my very introductory lecture in this course, is that there are these two types of processes, the mechanical type of processes, and then there is the things that are driven by entropy. This is one of those things which is sort of driven by entropy, in the sense that there's lots of reds, few blues, and hence there is a net motion from red to blue. And that kind of thing is best discussed by taking into account this right-hand side of the Boltzmann equation that we talked about in the last module of week 3. So when people actually derive, say, the Valet-Fert equation, they start from the Boltzmann equation. Okay? But in this course, of course, that's beyond the scope of what we're doing. That's not what we want to do. All we'll do is write this as proportional to mu up minus mu down and go from there. Okay? So now you can use this to obtain the Valet-Fert equation. The way it would work is the following. So d dz of I up then, and let me substitute from here. So what you'd get is d dz of I up, which is minus sigma a over 2q d mu up dz, and that is equal to minus k mu up minus mu down. And since this is a constant, I can pull it out from here. I guess I can take off the two negative signs from both sides, and I could pull this out. Let me take this off. I don't need this anymore. So what you'd get then is that sigma a over 2q d2 mu up dz2 is equal to k times mu up minus mu down. So we combine that to obtain this equation. Take this off, which leads us to d2 mu up dz2 is equal to mu up minus mu down times 2qk divided by sigma a. Okay. And I started with the mu up equation, the I up equation. I could have started from the d dz of I down, in which case I would have got a similar result, except that I'd have the d2 mu down dz2. This is the part I'm not going through because it would be doing essentially the same thing, but with the second of those equations. So if you did that, you'd get exactly the same thing, but with a minus sign there. Okay. So this would be the overall thing. And so you could write the following: d2 dz2 of mu up minus mu down is equal to, so d2, we have this and we have that, and if we just add the two, what we would get is mu up minus mu down times 4qk over sigma a. And this is the quantity right here that's often written as the inverse of the spin flip length squared. It has the dimension of inverse length squared, and so this is what you usually define as this the spin flip length squared. And the basic equation then looks something like this. We write it on top. This mu up minus mu down, that is this difference between the potential for the reds and the potential for the blues. That difference, that's what you often call the spin potential, as opposed to the sum of the two, which is more like a measure of the total number of electrons, or often you'd call it the charge potential. You see, all electrons have the same charge, but the red and the blue are have two different spins. So this difference is what you call the spin potential, and we'll discuss this further in the next module. But the basic equation then would look like d2 dz2 of mu s, which is the spin potential, which is up minus down, is equal to mu s divided by lambda sf square. That's the first equation. And if you wanted the sum of the two, then you can see what their answer is. One is equal to the negative of the other. So if we just took the sum, the answer would be 0. So if I just take the sum, what I'd have is d2 dz2 of mu up plus mu down is just 0. So to sum up quickly, so we can end this module, is that we have these two types of electrons, the reds and the blues, which we call the up and the down, and you have a mu potential for ups and the potential for downs. And if you look at the sum, then d2 dz2 of the sum is 0, just like we had before we talked about spins. That is, ordinary diffusion d2 dz2 of mu is 0. On the other hand, if you look at the difference between the reds and the blues, then it obeys an equation like this, whose solution actually looks like exponentials, and that's what we'll talk a little more about in the next module.